824 watt-hour per kilogram. If true, that number rewrites everything we thought was possible for EVs' range and weight. Today, I'm unpacking a dramatic lab result that just hit the headlines. A Chinese solid-state developer reported 824 watt-hour per kilogram in lab cells. That's not incremental, it's a jump. I'll explain what that figure means, how it stacks up against today's industry numbers and recent lab records. Run simple math so you can see the range and weight implications, and then walk through the hard reality checks. By the end, also, you can download a free PDF on this topic based on the link in the description. Manufacturability, safety, and the time it takes to turn a lab headline into the cars on the road. I'll point to the sources and give you a realistic read on whether this is a holy grail or hype. First, what was announced? Vilion, also reported as Vilion in some outlets, publicly stated in its R&D lab cells reach an energy density of 824 watt-hour per kilogram, and company leadership said they expect to push toward 1,000 watt-hour per kilogram in the long term. That claim came out via company statements and a televised interview with the chairman, and it's being widely reported across industry press. Now put that number beside what most of the industry delivers today. Modern commercial lithium-ion cells and packs used by mainstream EVs typically sit in the 200 to 350 watt-hour per kilogram window on a cell level and lower at pack level after mechanical and safety hardwares are added. Fraunhofer and other roadmaps put the common cell and pack level ballpark around 250 to 300 watt-hour per kilogram for many current designs, not the 800s. That means 824 watt-hour per kilogram, if it holds up and scales, would be several times higher than the average consumer products today. It helps to remember the difference between cell level and pack level energy density. Cells are the raw cells. Cells are the raw cells you see in the lab data. Once you add casing, cooling, wiring, BMS, structural material, and safety margins, pack level numbers drop often by 10 to 30% depending on the design. So a headline of 824 watt-hour per kilogram cell would still translate into a lower pack level number, but even a 20 or 30% drop from 824 would leave you well over 500 at pack level, still game-changing. Fraunhofer's roadmap and industry analysis explain these pack level overheads and why they matter for the real vehicles. We should also place this in the context of recent lab records. In 2023, researchers published a pouch cell result around 711 watt-hour per kilogram, which at the time stunned the field. That number was a research milestone, but not a ready-for-car product. The new 824 watt-hour per kilogram claims eclipses that earlier number on paper, at least in the lab conditions. Lab records have moved fast in recent years, but scaling and long-term durability remains the blocking step. Let's concentrate and do some maths, plain and simple, so you can see what this would mean for a typical EV pack. Take a 75 kilowatt-hour battery pack, a common size in many mid-range EVs. 75 kilowatt-hours equal to 75,000 watt-hours. If a pack averages 250 watt-hour per kilogram today, the battery masses would be 75,000 watt-hour divided by 250 watt-hour per kilogram, 300 kilograms. If a pack would use cells at 824 watt-hour per kilogram, the same 75,000 watt-hour would weigh around 91 kilograms. So simple division shows the mass drop from 300 kilogram to the 91 kilogram for the same energy. That's roughly a 70% reduction in battery weight for the same kilowatt-hour. Even after realistic pack overheads and safety hardware, the weight savings would be enormous and would change vehicle design, handling, and range math. The practical takeaway: if that cell level number translated into production pack numbers, you wouldn't just get more range, you'd get a fundamentally lighter car or much smaller pack for the same range. But here's the reality check and where the story gets complicated. Lab energy density records are important, but they rarely tell the whole story about the real world life viability. Here are major challenges, like supporting life cycle and cycle stability. A lab cell might hit a big watt-hour per kilogram at the start, but lose capacity quickly with repeated cycles or aggressive charging. Real EVs need thousands of cycles with decent retention. Safety and thermal behavior is also important. High energy cells often use lithium metal or other approaches that can be more volatile under abuse. Solid state electrolytes promise safety gains, but implementation details, interface stability, dendrite suppression, and manufacturing defects matter hugely. Manufacturing yield and cost also matter. Lab cells are often small and carefully made. Scaling to millions of large automotive cells demand reproducible processes and raw materials at scale. And early high energy chemistries frequently use expensive or scarce inputs. Pack level engineering is one of the coolers as well. Cooling, mechanical support, crashworthiness, and BMS complexities all add mass and volume. Scaling a lab cell into a safe pack often reduces the headline watt hour per kilogram. So while 824 watt-hour per kilogram is a spectacular on paper, each of those practical issues must be solved before buyers see 800 plus watt-hour per kilogram in showroom cars. Industry analysts and reports covering the announcement explicitly note commercialization and cost hurdles. The company itself suggested early applications may be in price-insensitive niches, not mass-market EVs immediately. Here is the core engineering problem. Energy density and real-world performance trade-off against longevity and safety. Pushing for extreme watt-hour per kilogram often puts you into chemistry and material regimes that are less tolerant of abuse. For EVs, you need a balanced recipe. High energy, fast charge capability, many cycles, safe thermal behavior, and manufacturability. The lab can optimize for one metric. Production cars must hit all of them simultaneously at an acceptable cost. A second systematic challenge is supply chains. If the breakthrough depends on the exotic materials or very tight manufacturing tolerances, scale up will be expensive and slow. In past, battery leaps, supply constraints, and massive capital investments have delayed mass adoption by years. Third, regulatory and testing timelines force caution. Even once a stable high-density cell is proven in R&D labs, automakers need repeatable evidence across many cycles, crash tests, and field conditions. That testing and validation takes multiple years, even in fast-track programs. Let's walk through what would need to happen for this 824 watt-hour per kilogram result to reshape EVs. Step 1. Independent verification. Researchers from outside the company need to reproduce the results or at least test the cells under independent cycling, safety, and abuse protocols. Lab claims alone are good for headlines. Independent replication in the gold standard is what we need. Step 2. Durability testing. These cells must show low capacity failed over thousands of cycles, stable temperature behavior under fast charging, and acceptable calendar life. That means repeating tests at different temperatures, different charge discharge rates, and under mechanical stress. Step 3. Pack engineering. Designers will need to create modules and packs that keep the cells within safe thermal and mechanical windows. Even if a cell has 824 watt-hour per kilogram, the pack might end up at 550 to 600 watt-hour per kilogram after necessary protection and structure. That still would be revolutionary, but not the original headline number. Step 4. Pilot production and yield improvement. Small pilot lines can test coatings, lamination, dry room requirements, pressure, and electrolyte handling. Yield percentage matters. Even a 5% defect rate at scale is catastrophic for cost. Step 5. Supply chain and cost optimizations. Alternatives to scarce materials or recycling loops reduce cost and risks. If the cell chemistry relies on the rare or expensive precursors, that can cap adoptions to niche markets. Step 6. Integration and vehicle testing. Automakers must validate how a new pack behaves in crash tests. In thermal runaway scenarios, under charging infrastructure variability and across climates. These steps are doable but time-consuming and expensive, historically. Moving from lab headline to automotive production has taken several years even for major players. The history of high-energy announcements shows a pattern. Lab breakthrough leads to cautious optimism, then it leads to many months of qualification, and then it leads to incremental product launches in the niche application. Then it leads to wider rollout if economics and safety checks out. The key moment to watch for is not the headline itself, but free confirmations, independent test data, robust cycling performance, and pilot scale production with acceptable yield. If the company or independent labs publish cycle life curves showing, for example, it's working more than 1,000 cycles with less than 20% capacity fade at realistic charge rates, that would be a major credibility builder. If pilot lines produce packs that retain more than 50% of the cell level advantage at pack level scale, then automakers could seriously redesign vehicles around the new packs. Right now, the announcement pushes the envelope of what's possible and accelerates the race. But it is a first step, not the finish line. Past lab records like the 711 watt-hour per kilogram pouch cells were huge technical milestones, but also highlighted the gap between the bench performance and full vehicle deployment. The same caution applies to 824 watt-hour per kilogram. It's a landmark to celebrate, study, and verify, but not yet a consumer-ready revolution. 824 watt-hour per kilogram reported in the lab test is the kind of number that gets engineers out of their chairs. It promises lighter batteries, impossible ranges, and new vehicle architectures. Compared to current commercial cells and packs that typically live in the 250 to 350 watt-hour per kilogram range, 824 watt-hour per kilogram is an order of magnitude leap. But big numbers need context. Pack overheads, cycle life, safety, manufacturability, and cost are the filters that turn the lab breakthroughs into the real products. Expect the next 12 to 36 months to be about verification, pilot productions, and early niche use cases. If the tech clears those hurdles, the EV market will look very differently. But that's a multi-year process, not an overnight switch. If you want a breakdown of this 824 watt-hour per kilogram battery pack, you can download the free PDF in the description. And if you want to go deep dive in the battery management systems in the electric vehicles, you can click on the BMS course links down in the description as well. Thank you.